So I'm Jonas from NOIA Network. I'm a CTO of NOIA Network. And since it's the last presentation in an innovation stream and it's before the coffee break, I'm not going to talk about a specific technology into very depths and not about a single product, but how a combination of technologies can transform internet and shape its future as we know it. But first, I want to give you a little brief of who we are, as Brian mentioned. So NOIA started as a distributed peer-to-peer CDN governed by blockchain. So we created a technology which allowed regular people's computers to share their spare capacity bandwidth, so we can cache data to their computers and deliver to the for the content providers to the browsers. We use WebRTC, and then the SDK can pull data piece by piece from different nodes and collect it back together in a browser and deliver the content. So we have many websites running already. We have more than 5,000 nodes downloaded, at least 300 nodes running every second, sharing hundreds of terabytes of spare capacity data. But then during the process, we figured that we analyzed how this data is being transferred from the nodes. And then we figured that there's a lot of inefficiencies in the core of internet itself, which cannot be solved by having more edges or having another overlay network. So we had to take a step back. And the step back is thinking how the internet really started. So if you think about it, internet is just really loads of cables. That's what it is. So it started when two universities connected together with a cable and sent some data. And then military networks joined as well, and they formed ARPANET. And then later, first major version of IP protocol was released, and that enabled some standardization and allowed other networks to join. And then telcos came and said, look, we already have cables laid out. Let's connect companies and home users. And this is how internet came together. And today it looks like this. So internet is now really thousands and thousands of independently operating networks, each with different quality, capacity, infrastructure, and even business relationships, and it became extremely fragmented. And the internet grew in a very decentralized way, so they allowed everyone to connect to that network. So that's why internet as we know it today was never designed, it just happened. It never had the grand design for the size of it, what it is today. So this fragmentation was built into the core of internet itself and determined the protocol designs. And you're probably all aware of BGP, right? So BGP is the protocol which needs to find any new IP address in the whole of internet without knowing the whole state of it. So what BGP does is it finds a new IP address with the shortest amount of network hops. So each BGP router is normally an ISP or a data center or an organization, and it governs its own network, and then it knows other BGP routers. So the problem, BGP is prone to ultimate design limitations just because the decentralized nature of internet. So first of all, forwarding decisions are based on the destination IP addresses only. So wherever traffic comes from, BGP just looks what's the shortest path to the destination, what's the least amount of network hops to the next destination. Then there's no control of routing path next hop. So, and remember, we're talking about public internet, not private networks. So once a BGP router sends and forwards the traffic, it can't do anything about it. It cannot, it cannot control what another ISP will do with that traffic, what peering relationships they have. Also, there's no link capacity and performance information. So BGP does not know what is the performance of a link 5 hops further. So it only looks how many hops until the destination. So a 90% packet loss link would be just as valid in a BGP's mind than a good link. Decisions based on static configuration policies. So BGP is normally configured manually, and those policies of routing stays until they're reconfigured. And it's fair to say that no static policy can be optimal when things change. Unselected routes are not propagated, so if you imagine internet is millions and millions of paths, and those who are not shortest to the destination are simply discarded. They're not being looked at. So that removes a lot of diversity from internet routing, which changes very dynamically. And ultimately, it's prone to IP prefix hijacking, which I'm going to talk about in a second, and I think what the previous speakers mentioned as well. So with the current internet, with the current problems, this internet architecture is deprecated. So we studied how internet performance, is doing, and almost all software providers, telecoms, operators, websites, broadcasters, they all suffer from internet-related problems. And it is impossible to guarantee service availability, service reliability without using overlay networks such as SDNs, private networks, MPLS, and so on. So on a public internet, you just can't rely on it. And what we found is that variation in latency is both very common and of significant magnitude. It's also large between different regions, both within and between continents. And what we found is that despite over time the internet infrastructure is improving, so there's more throughput, more capacity, we have 4K, etc., but the variance of that performance remains. And another interesting problem is that the current internet architecture is just inherently not secure. So internet suffers from BGP hijacks daily, and a recent and interesting example is Bitcoin network. So by one of the recent papers, it turns out that you can turn down or hurt the whole Bitcoin's network by using BGP hijacks. So a BGP hijack happens when a bogus ISP or a bogus BGP router just announces ownership of the IP addresses. And because of the decentralized nature of internet, that just propagates often around the world, depending on the importance of that BGP router. So it turns out that you only need 13 ISPs and less than 100 IP prefixes announced by the attacker to take the very large chunk of the whole Bitcoin's network. What you can do with that is you can route traffic through the attacker, and everything will work, or you can just stop those packets, or you can impersonate a website. And there's hundreds of thousands of BGP hijacks happening every month, with the most popular examples being 25% of US traffic going through China Telecom for 2 months unnoticed, and Google's traffic going through Russia for the whole hour before Google could take back of its control of its IP addresses. And my favorite is that Cloudflare.com on their very website just says BGP was not designed with security in mind. And it's pretty much nothing you can do just to react as fast as you can. All these problems cost $700 billion a year in outages for enterprises and businesses, according to a recent IHS study. And that's primarily due to internet service disruptions. So these costs add up not only by SLA agreement breaches, but only through lost productivity, user experience, and so on. So that's a huge amount of problems being caused. So you might think, what's the world doing about all this? And you might as well know IPv6, and that's one of the initiatives the internet governing bodies are doing. And what basically the main two parts in my context for IPv6 is that it allowed way more IP addresses, obviously, but it expanded the packet design to have more headers and have custom headers in each packet. And then Internet Engineering Task Force, using that feature, came up with segment routing. So I wanted to ask, who's here heard of segment routing? Right, finally something new. So segment routing is a protocol which makes routers understand routing information from the packet headers. So it basically allows you to put the full route a packet needs to go into the header, and the routers understand it on the third layer, on the routing on the router itself. So it's being developed since 2014 and is now being picked up heavily by Cisco. And Cisco is already saying that segment routing will be the next wave of how SDN networks are being created, and that will lead the next disruption in networking. So what segment routing does is it allows, as I mentioned, routing information to be added to the packet header. So then you can program the data to take a certain path. And in a simplified example, so if you have a node, so you can either have IP addresses on a public internet, or you can have on an IPv6 network, or you can have node IDs in your private segment routing network. So if you have a packet and it says deliver it to 16.0.0.6, it will go via shortest paths to 16.0.0.6 via BGP, same way. But if you encode into the data 16.0.0.4, which is here, first it will send that packet to the next segment. There can be many routers in between, but it will send that packet to the next segment. That router will remove itself and send it to the next segment, which was 16.0.0.6. So sending two different data packets with different routing and coding into the packet header, segment routing enabled routers would route it differently. And there's many more features about segment routing itself, but that's a topic on its own. But you can have fast rerouting, which reroutes if a link is dead somewhere here. Segment routing can reroute it within 50 milliseconds and have another route. And they can have different policies. They call it collars. So you can have a minimal latency path, or you can have zero packet loss path, and have certain criteria to choose a path for your data. So you might think, so how we can use all those technologies to solve the problems I was mentioning. So the concept I'm here to talk about is programmable internet. So the ultimate solution is to be able to access every router in the world and program the data so that all those routers would understand how to route it and use standardized protocols. Now, how is that all possible? So the first step is standardization. So as you can see, IPv6 adoption is growing and is set to be more than 30% in a couple of years. And it's already huge in private networks and in between data centers, etc. But the problem is really the end users who remain still primarily on IPv4. And segment routing is being adopted heavily and very quickly. So Cisco is already having their latest routers supporting segment routing by default. Linux kernel supports it now. There's open source virtual router, which we use. And there's Barefoot, and even Juniper's is set to have segment routing support in their latest chips. And segment routing extensions are being added to existing protocols and IGPs, etc. And you can also use segment routing, segment IDs in MPLS networks. So the world is really ready for programmable internet. Routing hardware is largely capable of supporting segment routing already. So this means that hardware standardization will allow private network features on a public internet, because you can have access to independently operated networks. You can have common set of internet routing rules which each router understands, and then you can merge the control plane into data plane. What I mean by that is that data becomes smart and routers become standardized. Instead of routers with software layers on top making routing decisions, you have standard routers and you have data being smart and knowing where it needs to be routed. So in a regular, everyone in networking is probably aware of the 7 layers of network stack. So then usually in a private network or an SDN for any smart network, when a packet goes through physical layer, network layer, needs to look at its transport, either it's TCP, UDP, it goes all the way up to application layer, which is OpenStack, OpenFlow, or anything else, and goes back with its next routing decision and goes to the next router. What you can achieve with segment routing and standardized hardware is the packet comes to the router, packet has route information in its header, and the router just forwards that packet to the next available segment, skipping all of that layer and making new SDNs or private networks more lightweight. At the same time, if you have it on a public infrastructure, you can have private network features on it. Now, you don't need to have every router segment routing enabled to make this reality. In fact, in between segments, packets go via standard shortest path. So all you need is one router, and you can already split the internet in two paths. So if the shortest path is here, if you just send a regular packet, it will go on the shortest path. If you have one segment routing enabled router in an IPv6 network, you add those segments to the data, and here we'll split and take this path. So you don't need every route. You know, there's always a chicken egg problem in huge innovations that it's hard to change something which is already very established. You can't just take the whole internet down and bring up a new one. But with these technologies, it can happen gradually because you don't need every router available at the beginning. Now, the problem with that is, if you want to route something in a smart way, you need to know what is available. You need to know which routers can you route through. Because on a private network, you control your infrastructure, so you have that. On a public internet, and that's why BGP design was influenced by the decentralized nature of it, that BGP does not need to know the whole network state. It's just too big. And there was never a place you can have a single source of truth of the whole internet's topology and keeping it decentralized. So there is no central point. Even now on the internet, there's no central point of all the IP addresses or its topology. So with the coming of distributed ledger technology and blockchain, there's now an ability to have a database, a single source of truth of every participating router and information needed for routing, but keep it decentralized, keep it of high performance, and keep it both architecturally and politically decentralized, because you can use consensus protocols in a distributed ledger, and you'll have always the same information, but the database will be spread apart, and it won't be controlled by anyone using blockchain consensus protocols. So SRv6 and distributed ledger gives you the knowledge of the whole participating router's topology, and the technology and standardization, which allows you to use that topology to make decisions how do you want your data to be routed on a public internet. Now, the last missing piece is, why would you do that? Why would anyone, a telco or a router or a DC, why would anyone allow their infrastructure to be open and then let anyone pass data through it, because it costs money? And here's the last missing piece. So distributed ledger technology allows you to have a decentralized internet exchange. So you can have Ledger with all the IP addresses and participating routers, which come onto Ledger to sell their infrastructure through smart contracts. And the decentralized internet exchange allows you to buy and sell internet access points as transit anywhere in the world. So currently, internet providers, and they can only sell and buy internet transit only with who they have a direct cable connection with. That makes sense. Or they can syndicate, and they can have, they can buy full routes by having agreements between telcos, etc. But you can always trade with only someone you have a cable with. With this concept, you can buy an access point. If you want to send data from Frankfurt to India or somewhere else, you can buy several access points. You only need to steer at your almost last mile where you need to transfer your data. And because you can trust that transit's okay until here for your purposes, and then you just buy a couple access points, and then your traffic goes through there or not there. Because now you can control how your traffic acts at the end of its journey, as opposed to, the hot potato BGP is always playing. So on a decentralized exchange, you can secure a full route, or you can buy any access point to send your traffic through. And then you can have authorization, via IPsec, and there's many technical details about it, but you can buy and sell your internet transit as access points. That also allows infrastructure providers and data centers to sell individual pieces of infrastructure through the exchange. Because now if you sell, your whole backbone or network, you sell it as a black box. with a decentralized internet exchange where you can sell not directly to your neighbors, but anywhere in the world, you can split your infrastructure and sell individual pieces as transit because someone might need exactly that piece of transit. So who we are in all this process. So NOIA Network is an initial network in the programmable internet. So first, we are building a SR and IPv6 enabled network. That's the first IP SRv6 network. And we have a platform for programming segment routing. So you can program those headers, you can select the fastest path, zero latency path, you can have your custom paths, and then you can use our SRv6 network as a service, as a business for your needs. At the same time, we're launching a distributed ledger and an decentralized internet exchange for anyone to sell and buy internet access points and use either our controller or any other controller to program the data. So if there's any of those access points available, you can send your traffic through them. So to expand on the network we have, so as I mentioned, it's an SRv6 network. We're early in the game adopting segment routing. And if you have your first mile with the offices and ISPs and your last mile in data centers, that's where all the investments go, you often overlook the transit, which is a very important part of the internet, but it's just not getting as much investment in terms of improvement. So we build a network from our partners, data centers, and multi-cloud infrastructure, and we sell global NOIA backbone, a segment routing enabled network as a service. And then the platform itself is a platform where you can self-onboard and have a connection between any two IP addresses. So either it's a server-to-server connection, server-to-game or application, so you can have a single server and gamers from Taiwan and Estonia playing on the same room. They connect to our edges, and then we deliver traffic to the gaming server in the best possible route using segment routing. And it also has a network function marketplace where, an interesting part in segment routing is if you put an IP address in one of those, in one of those segments, it will go through that IP address. But that IP address can be a server, an encoder, any other network function. And so by sending traffic through, we can just make a stop and an encoder, get that traffic back and send it already encoded or encrypted or zipped, etc. And this is it. This is how programmable internet looks. So it's a network by anyone's public internet infrastructure. It's a ledger and a decentralized internet exchange where you can buy and sell that infrastructure. It's a consensus protocol which keeps this whole process decentralized and keeps internet decentralized. It's our controller to program the data to use those features or any other controller. And there's smart contracts doing the authentication. And yeah, so to conclude, thank you. Please come talk to us. We're happy to talk about blockchain and technologies, and we're always looking for partnerships and technology friends. So please do come talk to us, and thank you very much for your attention.
Thank you, Jonas.